Hi, future chemists at Research Triangle High School. My name is Mrs. Moore, and today I'm here to teach you about the stoichiometry of volume of liquids by way of density as a conversion factor. So by the end of this video, you should be able to calculate the volume of a liquid by using density from particles and from grams, as well as go back to grams and particles when given the volume of a liquid. So far in stoichiometry, you have learned that to go from the volume of a gas to moles, you use the conversion factor of 22.4 liters is equal to 1 mole. But remember that it's only usable for a gas, so there has to be another way to calculate the volume of a liquid, and there is. So welcome density to this long party. So density can either be calculated as grams per centimeter cubed for solids or grams per milliliter for liquids. So that means if given the mass of a substance, you should be able to calculate the volume of that liquid by way of using density. You will be given grams and you will be given the density. So just by using a conversion factor, you should be able to determine the volume of that liquid. So let's look at some examples. So the following equation represents the rusting of iron. So 3 oxygen gas plus 4 solid iron yields 2 iron oxide solid. So assuming that all STP is the same, what volume of oxygen gas will be required to produce 16 grams of iron oxide? So typically, this is a type of problem where since you're using oxygen gas, you will continue to use the 22.4 liter is equal to 1 mole conversion. So you already have the 16 grams of the iron oxide. And we want to get to the volume of oxygen gas. So knowing that you have 16 grams of iron oxide, you now can calculate all the way to the volume of oxygen gas. So starting with grams, we are going to put the molecular weight of iron oxide on the bottom, which would be 50. So the molecular weight of iron oxide is 159.8 grams of iron oxide. And that is per 1 mole of iron oxide. Next, we determine the mole-to-mole ratio. So you have moles of iron oxide on the bottom, which if you look at the equation, that would be 2 moles of iron oxide. So what we want to go on top, and since we're looking for the volume of oxygen gas, the mole-to-mole ratio would be 3 moles of oxygen gas on top. So now that we have the moles of oxygen gas, we can use a 22.4 liter conversion that is equal to 1 mole. So on the bottom you will write 1 mole of oxygen gas is equal to 22.4 liters of oxygen gas, which is true. So now when you do the total calculation, that equals 3.36 liters of oxygen gas. So this is how you would do the example with using a 22.4 liter conversion factor as you've learned so far with oxygen gas. But what if you wanted to calculate the volume of iron? And iron here is a solid, so how would you do that? This is where using the density factor will come into play. So the problem says, what volume of iron would be required to produce 6.43 times 10 to the 24 molecules of iron oxide? The density of iron is 7.86 grams per centimeters cubed. So we're starting this problem off with 6.43 times 10 to the 24 molecules of iron 3 oxide. So since we have that first, we're going to have to use Avogadro's number to place on the bottom to calculate to the conversion factor of the number of molecules that is equal to 1 mole. So 1 mole of iron 3 oxide on the top and 6.022 times 10 to the 23rd molecules of iron 3 oxide on the bottom. So our next step will be to use the mole-to-mole ratio in the equation. So what are we going to? We're trying to calculate the volume of iron from the molecules of iron 3 oxide. So the mole-to-mole ratio would be what you have on the bottom and what you want on top. So what you have on the bottom, and based on the chemical equation, is 2 moles of the iron 3 oxide. And based on the equation, the molar-mole ratio will be 4 moles of iron solid. So now that you have the molar-mole ratio, what do we do next? So remember, based upon the schematic from the first slide, we now are sitting at the mole. So next we're going to convert to the molar mass, or grams. So we know that we have 1 mole on the bottom of Fe, or iron, and the molecular weight of iron is 55.9. So we place 55.9 grams of iron on top. Remember, here now we're at the point where we have the mass in grams. And so now we're going to use density here to get us to the actual volume. So back to the equation or the given problem, it told us that the density of iron was 7.86 grams per centimeters cubed. So that's what comes next. So on the bottom is grams per centimeter cubed. So what we have is grams, and we want to end up with centimeters cubed. So on the bottom, we're going to put the 7.86 grams, 8.6 grams on the bottom. And on top, that is 1 centimeter cubed. So once you do all the calculations, that equals to be 151.9 centimeters cubed of Fe. So that means that you would need 151.9 centimeters cubed of iron to produce 6.43 times 10 to the 24 molecules of iron 3 oxide. So that is how you calculate the volume from a solid. But what if you want to do it from a liquid? So we have another example for that. Okay, so in this example, the question is asking how many liters of liquid bromide are needed to react completely with 267 grams of calcium iodide. And the density of liquid bromide is 3.12 grams per milliliter. So thankfully, this equation is already balanced for us, so the molar-mole ratios throughout this whole problem will be only 1. So if we're starting off with 267 grams of calcium iodide, and our goal is to get to how many liters of liquid bromine. So first thing we're going to do is convert from grams to mole. So the molecular weight of calcium iodide, 293.88. So 293.89 grams. So that's the molecular weight of calcium iodide. And then you have 1 mole of calcium iodide on top. Next, we want to go to the mole to mole ratio. So what we want goes on top and what we have on the bottom. So we have moles of calcium iodide. So 1 mole of calcium iodide. And what we want is the moles of liquid bromine. So on top, that is again 1 mole of Br2. So next, since now we have moles, we can convert over to grams. Because remember in this schematic before, it told us if we have moles, we could go to grams, and then from grams, we could use density to calculate the volume of liquid bromine. So now we have 1 mole here, and we want to go 1 mole on the bottom. And on top will be the molecular weight of bromine, which is 159.8. Now that we have the grams, lastly, we can use the density to calculate the milliliters of liquid bromine. So on the bottom, we have grams, so we want to keep grams on the bottom. So 3.12 gram on the bottom, and on top, it will be 1 milliliter on top. Okay, so now that we have all of that written out, let's figure out what the final calculation is. So the final calculation comes out to be 46.5 milliliters of liquid bromine. However, the question tells you that you want this answer in liters. So, already knowing how to convert from milliliters to liters, you move the decimal point 3 places to the left, which would give us a final answer of 0.0465 milliliters of bromine. That is what is required in order to completely react with 267 grams of calcium iodide. So now we showed how to go from grams to milliliters or grams to liters. How about if we start off with milliliters? So the next question says how many grams of calcium iodide are needed to completely react with 15 milliliters of liquid bromide. So if we're starting off with 15 milliliters of bromide, now here we have milliliters, but we are trying to get to grams of calcium iodide. So now we're going to use the density in the very beginning instead of at the end. So remember, what you want is on top and what you have is on the bottom. Currently we have milliliters. So the density of liquid bromine is 3.12 grams per milliliter. So 1 milliliter on the bottom, 3.12 grams on top. Next, we have our grams already. So we're going to convert our grams of bromine to moles of bromine. So you're going to put the molecular weight of Br2 on the bottom, which from the previous question we know is 159.8 grams of bromine on the bottom, and on the top is 1 mole. Now we go straight to the mole to mole conversion, which again, what we have goes on the bottom, so 1 mole of Br2. And what we want goes on top, which we're looking for here, calcium iodide. So 1 mole of CaI2. Now that we have moles, we want to calculate the grams of calcium iodide. And on the bottom, again, is what we have, which is 1 mole. And on the top is what we want, which is the molecular weight will go on the top for grams, which we already know from the previous problem is to be 293.89 grams of calcium iodide. And now let's see what the final answer is. So our final answer is 86.07 grams of calcium iodide needed to completely react with 15 milliliters of liquid bromine. So now you know how to go from grams to milliliters and from milliliters to grams, and both doing so by using the density.